All right, so welcome everyone to your Thursday evening dose of astronomy. I'm Irene Pease with the Amateur Astronomers Association in New York City. You can find us at aaa.org and follow us on all the social media things at AAADOTORG. Tonight, as usual, we'll be using a couple different programs. We're going to be using OpenSpace, which you can find at openspaceproject.com. You can download it for free. They just put out a new update, so I'm excited to play with that over the weekend. That's what I'll be doing. What are you going to be doing? I don't know. It's up to you. But it's free. It's freeware, and I'll say a few more words about the visualization program a little bit later. We're also going to be using Stellarium, which you can also download for free at stellarium.org. They also have an app, so I highly recommend that as well if you like what you're seeing here tonight. So tonight, I just kind of looked in the calendar and I said, what happened in history this week? And it turns out there were some explosions. I was like, I'll do explosions in space. There's a kind of a historical explosion that happened in 1054, so that's your first hint. Some people might know what that's happening. What's that about? So we'll get to that in a little bit with more of the open space, but I like to start off with, what's up in the sky. So we want to know, if I walk outside tonight and it's not cloudy, what am I going to see? Well, so let's check that out. So we're going to start off with Stellarium here. This is set for now, and it's pretty bright out. Again, we're just a little bit past the solstice, so still bright. Sun hiding behind that giant tree. Still haven't chopped that one down, virtually or otherwise. But let's go ahead and fast forward a little bit to when it's actually dark. So we're going to go all the way till 10 o'clock, because I actually want it to be pretty dark for some of the stuff I want to show tonight. So before I get to the explosion stuff, there's some other things happening. So we're going to do, this is going to be kind of a two or multi-parter, looking at some comets. So there's comets out and about in the skies, morning and evening. So I just want to give you kind of a preview of where you'll be seeing those. They may not be super visible this week, but more next week. So we'll follow up, but I wanted to start off just kind of showing like where you're going to be looking in the sky so you can get familiar with those parts of the sky. So one part we've talked about in the past already, over near Virgo and the bright star Spica. So if you look over towards the northwest-ish, way up in the sky, you see the Big Dipper, right? So the 3 stars in the handle and then the cup. So we follow the handle. We said we arc to Arcturus. So remember that was in Boötes, the ice cream cone. So you arc to Arcturus and then you speed on to Spica. So that kind of bluer star. So last week when we were looking at star colors, I said Arcturus was kind of like a little bit of a yellowish hue, and Spica is more of a blue hue. So I don't know if you got a chance to see those this last week. If you didn't, go ahead and find Spica again this week, because in the coming week or so, there's going to be a comet kind of putting along, not quite through Spica, but through another part of that constellation. So I'm going to go ahead and bring up the outline of the constellations. Virgo is not a super bright constellation. But that's where we're going to be looking for where we're going to be looking for a comet in the evening next week. So if you can find Spica, try and pick out kind of the this other kind of trapezoid part of Virgo. And I know it's going to be harder to see some of these other stars that kind of jet off kind of to the northwest of that trapezoid, because they're going to be fading into the glow of the horizon. You might also recognize Leo very close to the horizon. So see if you can pick those out this week, the parts of Virgo that are between Spica and Leo. And we're expecting a comet to be kind of coming through here in the coming weeks. So it'll be kind of just booking it along there. So not too bright yet this week. Lost my map, but if you don't see it later this week, we'll take a look and I'll show you more of that next week. So be looking in that part of the sky. We have our moon out tonight. Yay! We'll do the moon more another time. Like I always say, everything's going to happen another time. The other part of the sky, I guess you want to get to know a little bit better, is actually up in the morning. So if you're up for a challenge and you're a morning person, you can go ahead and try and find this other comet in the morning, and then next week we'll talk about finding it in the evening. So when I say morning, I mean like really early morning, like before the sun, because once the sun comes up, it's too late. You're not going to see anything. So if you're up early, like 4 a.m. ish local time, the really bright thing in the east is going to be Venus, right? So you can't miss it. Venus is super, super bright. We saw it in the west in the evening in the last few months, but now it's up in the morning. So that really bright thing up in the morning in the east, it'll be a little bit north of east. And then further north from there, we have this kind of pentagon shape. Oops, ignore that. We have this kind of pentagon shape that is going to be just right on your horizon there. So there's a bright star, Capella, and there's a comet that's kind of zipping along here, and it's going to be zipping up this away towards the north. And so if you can catch it either tomorrow morning or maybe Saturday morning, basically before the moon is like too close, because the moon is really bright, like it's almost full. Remember that moon? It's just set here. So if you can go out either tomorrow morning, or if we do this early Saturday morning, that really bright, almost full moon is still going to be there. So that's going to produce a little bit extra light and make it harder to see the comet. So we'll look and see where it's going to be in the evening next week. But if you want to try and catch it in the morning, there you go. There's a little challenge for you. So as far as explosions go, we wanted to show you one of the most energetic events in our galaxy that we have. Those are supernovas. So those go off every now and then. Every 100 years or so, you get like a big one in a galaxy. That's kind of the accepted average. So we want to show you the one that went off about 1,000 years ago in 1054 that produced the Crab Nebula, which is out in the wintertime. So we can't show you that. But that one was really cool. It was observed all over the world. So we see records of it in all different cultures from around the world. People going, yeah, there was a really bright thing. Like it was so bright you could see it during the daytime. So like hard to miss. But there's another supernova remnant, so just the leftovers, just this gas expanding out into space from this super huge explosion that happened about 10 or 20,000 years ago, that's up in the summer sky. So I think last time I mentioned the summer triangle, which is these 3 stars from 3 different constellations. So if you're just looking off towards the east and very high up, that really bright star, kind of whitish blue, that's going to be really, really high in the sky towards the east, that's Vega. So that's the westernmost part of the triangle, and the rest of it is back here towards the east. So you have the star Altair, which is in the constellation Aquila, and then the star Deneb, which is in the constellation Cygnus, which is where we want to be. So if you can find that triangle, Deneb kind of lines up with these other stars to form kind of the body. That's Deneb is the tail, and then you have this long body, long neck of the swan. I think we may have looked at Alberio last week. See those brilliantly different colored double stars there, and then it has like these wings that go out. And oh look, there's a satellite. Nifty, not a comet, just a satellite up there. So these wings that go off on either side, the ends of the wings are much fainter. The central part, which we also just call the Northern Cross, these stars are a lot brighter, but if you're in a dark site, you can see the full wingspan of the swan. And if you're in a really dark site, you can see it's basically flying along the Milky Way. So kind of along here where the swan is pointed is the plane of the Milky Way as seen from Earth. You're probably not going to see it too well tonight between the moon and whatever sky glow you might have. But if you can find that swan, so find your triangle, see if you can find the swan, and under the or above the eastern wing of the swan, you can easily pick this out with binoculars, and in a dark sky you can see it just with the unaided eye. This little star here, 52 Sig. So if we zoom in there, we can see this glorious bubble. This is the Cygnus loop. So 2 different pieces of what we might call the Veil Nebula. So this is leftovers from some huge star that exploded, just exploded. It was at least 9 times the mass of our sun. Anything that's more than 9 times the mass of the sun can go supernova at the end of its life cycle. This star we think may have been 20 times the mass of our sun, so, you know, big. So when it used up all its nuclear fuel, it just exploded. It's a little more complicated than that, but I didn't want to get into the mechanics of supernovas. Just mentioning that, yeah, we have these supermassive explosions in space, and there's other types of supernovas, but this is from just one huge star that used up its nuclear fuel, imploded and exploded. So all this gas has been expanding out to space for, like I said, about 10 or 20,000 years. And in the next 10,000 years ago or so, it'll kind of slowly dissipate and fade away, and then collect to form the next generation of stars. So that's where we get all the bits and pieces of the universe that are not just hydrogen. So we have a lot of other elements besides what we got just straight out of the Big Bang. A lot of those elements, well, all those other elements are formed in stars, and I actually wanted to show a quick picture of that. Just seeing Chris's question about the tail of the comet. I don't recall. I have my maps here somewhere, but I will get into more of that next week. If you check, there's a really good article, I think, in Sky and Telescope about it, and I'll try and post a link in the comments or in the description afterwards, so you can get a preview of that. So let's go ahead and take a look at some OpenSpace, and I want to talk more about these explosions, and I actually wanted to share this one of my favorite periodic tables. So if you've ever taken chemistry class, you know, you recognize periodic table. So this is like an astronomy periodic table showing the actual sources of all these elements. So there's a handful, right? So like hydrogen, helium, and I feel like there's like a tiny bit of lithium, but I don't know, it's not colored in there, that were from the Big Bang, right? And I'll get to that one too. And then a lot of these, everything else is like made in stars, basically. So our sun can burn things like all the way up to eventually iron. So we have some stuff that's made in small stars, carbon, nitrogen, oxygen. You have your CNO cycle, and some of these other bits. And then we have things made in larger stars, like so all that green stuff. Like so heavier stars, like the star that this thing was before it exploded, could have burned and created all these other exciting elements, technetium, tungsten, zirconium, good stuff. But it's not until they go supernova that we get everything else filled in. So that's a lot of stuff. And then there's like the, I don't know, artificial whatever stuff, purple. So yeah, so that's where a lot of material, different types of material, the variety of material that we have in the universe comes from stars exploding. So that's pretty great. So where can we find exploding stars? We're going to see kind of what they would look like as viewed from Earth. So let me bring up our supernova remnants. So we have a few of those around, not too many. But I'm actually going to go ahead and pull away from the solar system here. And yeah, so comets, just as we're moving out, comets and comet tails, comets generally have 2 tails, and the brighter one, the dust tail, will be pointed away from the sun. So yeah, if you know where the sun is, it should be, yeah, directed away from that. And then there's an ion tail that's exactly away from the sun, and then the dust tail is like curved a little bit, if I remember right. I'll brush up and we'll get back to that one in a little bit more detail next week. Detail of where all these comets are. So, but yeah, moving out far away outside of our solar system, out into the Milky Way galaxy, so we can see kind of where these objects are in the galaxy. And I'll go ahead and just turn on our constellation lines to leave as a marker. That is where we are. Okay. So these are the supernova remnants again. So those huge clouds of gas that were blown out, all this material that was blown out of a really massive dying star, expanding out into space. And again, they are relatively short-lived, so we don't see that many of them. So I mentioned the Veil Nebula, this one that we looked at just now in Cygnus, and then the Crab Nebula, that's out more like in the winter time, and that one's a little bit more recent. But because they expand out, they expand freely for just a few hundred years, and then they start to like run into enough material between the stars, what we call the interstellar medium. So it's not a perfect vacuum. There's other dust and gas and stuff out there, but running into that other material will slow them down, and after another 10 or 20,000 years, they kind of like come to more of an equilibrium and just start to cool off. So it takes a little bit longer then for them to cool off. So compared to like other things in the galaxy, they don't last for that long. So if we look at what's left over, so there's all this gas expanding out to space, but then in a supernova explosion, there's a compression that happens first, a compression and then an explosion, and in that compression, we get neutron stars, which may also end up being pulsars. So last week I had the pulsars in this brilliant purple. The purple didn't show up so great, which is why they're not supposed to be purple. So I changed them back to their original red. So you can see a bunch of these red dots in here. Those are all the pulsars that I talked a little bit about last week. Very, very high energy. Basically, a neutron star is just going to be like a super, super, super dense core, kind of like a giant atomic nucleus, like the size of a city. And if it has a strong magnetic field and is rapidly spinning, then it gives off these jets of radiation from its magnetic poles. So as it's spinning, it like pulses. Those jets will pulse towards and away from us, hence pulsar, because astronomers are naming things. So we see that the pulsars aren't all exactly in the plane. They're not as confined to the plane as the supernova remnants, but if we consider that, most of the stars are in the plane, and so when they explode, they're going to be in the plane. But we do have several that are, eventually will migrate. So the star that would be at the core of these supernova remnants could be pulsars or just neutron stars or even black holes. Ooh, even more exciting. Those can migrate and, end up not necessarily just in the plane. So supernovas give off a lot of energy. I mean, enough to blow this gas out into space for, a few thousand light years, just kind of shoveling stuff out of the way. They can be bright enough to outshine an entire galaxy. So that's a lot of light. That's a lot of energy that's happening. So those are actually things that we can see in other galaxies. So I'm actually going to move out a little bit further now, and we're going to leave our galaxy and look at other galaxies. So say goodbye to the Milky Way. We should have a whole nother data set coming on that I've mentioned before. Here we can see we have our two neighboring galaxies, Andromeda and Triangulum. So that's part of our local group, I think we've seen in the past. But then moving out into what we call the Tully data set. So there was our little group, just a, kind of a little clustering there. But out here, we have, there's about 30,000 galaxies or so in this data set, so a lot. We can see where there's a supercluster, so our local cluster over here, Virgo supercluster. So that's where that relatively recently, I guess it's been over a year and a half now, we imaged the black hole in the center of M87. So M87 is part of that cluster in there. But yeah, so we can see supernovas going off in all these nearby galaxies if they happen. And, every now and then in the news, there's a supernova that goes off in like a known galaxy. Like there've been some in the Whirlpool galaxy that a lot of people like to look at. And in M81, M82, I don't remember, whichever one is the Cigar galaxy up by Ursa Major. That was a couple years ago. So I've actually had a chance, if you're an observer, and we have some observers that listen in, you may have seen, some of these supernovas that go off in relatively close by galaxies that we can observe with amateur telescopes. So that's pretty neat. We can actually use those to measure distances to those galaxies if it's a certain type of supernova. And if you're taking one of the AAA classes, one of our summer classes, shameless plug, well, if you're taking the class that's happening right now, you're not in class right now, so I don't know what's up with that. But but one of our classes right now is talking about how we measure things in space. So if you want to learn more about that, take a class. We have another class starting next week that I'm teaching, Astronomy 102, and I'll talk just a little bit about that, not in as much detail as the astrometrics class that's happening right now. So these supernovas, huge explosions, can outshine a whole galaxy, and we can use those to measure distances to other galaxies. The other things that I just mentioned that we have in other galaxies are these black holes, though. So what I wanted to do is actually move out a bit further, and these are all, I think I wanted to show, yeah, I'm going to skip that one. I wanted to show past these galaxies, we have, well, more galaxies. So we're getting pretty far out. This is about, not quite a billion, getting outwards around 1 billion light years away from Earth, from home sweet home that's there in the center. Every dot that you're seeing here is not a star. These are all galaxies, right? So we've plotted the positions of a lot of galaxies. Out here we can see kind of the large scale structure, kind of this webby texture where like the superclusters of galaxies are clumped together, and then we have huge voids between them. But these are all galaxies. And what do we have besides galaxies out here? Well, we have these other super fascinating, very energetic things that we call quasars. So that's the other thing I wanted to show. So I'm actually going to turn off a bunch of these galaxies, say goodbye to the Sloan Digital Sky Survey galaxies, and we're going to turn on some quasars. So quasars are quasi-stellar radio sources or quasi-stellar objects, and they're far away. Galaxies are all around us, right? So we live in a galaxy, there's nearby galaxies, there's these distant galaxies, but I just turned on, I said we're about 1 billion light years away. The quasars are out past that. So the nearest quasars to us are like 2 or 3 billion light years away. Those are the close ones. Billion with a B, all right? So remember the Andromeda galaxy, like our cozy neighbor in space, and our local group, that was just a couple million, right? So this is 1,000 times further away than the Andromeda galaxy is. So the interesting thing is, one, these are very, very bright. We shouldn't be able to see these from so far away. I mean, they shouldn't be, what even makes things that bright? So there's a lot that we don't actually know and completely understand about them. We think that these really, really bright sources of energy are powered by supermassive black holes at the centers of galaxies. So we know we have a supermassive black hole at the center of our galaxy, but it still is kind of like dwarfed in comparison to some of the other supermassive black holes in other galaxies, like the one that I mentioned we'd imaged in M87. But they give off so much energy. They're about 100 times, basically 100 times as bright as our entire galaxy. So if you take all the light that's coming off of the Milky Way galaxy and had like 100 Milky Way galaxies all crammed together at like a single source, that's how bright some of these quasars are. Like, what even does that? So again, we think it might be material infalling and then getting heated and excited and ejected off of the disks around super massive black holes. But we can't get too close because again, they're far away, which if you have studied like light travel time, we know that light takes time to travel, right? It doesn't just happen instantaneously. Light travels really fast. It's our universal speed limit, but it still takes time. And get too far out there. So if we're looking at things that are far away, that means we're also looking back in time. We're looking at things that happened long ago. So we don't really see quasars in the local universe. We don't see them in the present. They're not out today. Sorry, we're just like in this massive cloud of quasars. There's so many quasars. So these are kind of like relics. They're like fossils from like the early universe that have somehow, I don't know, faded, morphed into what we see, evolved into today's like present galaxies, what we see closer to us. So I just think that's like fascinating to see like the kind of the evolution of the universe. That yeah, there used to be all these like really, really energetic things at the centers of the large galaxies, just giving off so much energy. Pretty exciting stuff. So we don't have that anymore, but you know, back in the day. So yeah, so as we're looking at this structure, we have kind of a similar, I call it like a butterfly structure-ish, these kind of lobes in the data set. They were kind of less distinguished lobes in the earlier data set that I was showing with the galaxies, and you have kind of these spikes going out. But yeah, that is in fact an artifact of our observation. So there's this region, if I can pause it, that we sometimes call the zone of avoidance. I can get at it. Yeah, there we are. Here's our zone of avoidance. So it's not that we don't want to look there, it's that we can't. So this is basically the plane of the Milky Way galaxy. So if I blew up the Milky Way galaxy really big, it would streak across here, right? So that would be the disk of the galaxy, and then looking either this way or this way towards where we see those lobes, that's looking out of the plane, like above or below it, so to speak. So it's really hard for us to see beyond our galaxy in this direction, just because there's so much stuff in our galaxy in the way, like all the stars and gas and stuff. So we're mostly looking out of the plane. So yeah, so that's where we've looked. And because we're seeing basically the same thing in all the different directions that we're looking, we can assume that if we were able to see out through all the gas and dust and stuff in our galaxy, we would see the same thing there. And you can see it's almost like sheets of data here. So they do these all sky surveys, or not all sky surveys, but they might do like 2 degrees or 6 degrees where they just kind of scan one swath of the sky. So then when you move away from that, it kind of fans out into this shape. So it's kind of a neat to see, like, yeah, that's basically the data set, that it looks like one point or like a little block or a rectangle on our night sky, but then we move out into 3 dimensions, like we can see, like, you know, that 3rd dimension, like some things are closer and further, so it has like this neat shape to it. So I didn't want to come all the way out here and be, you know, talking about explosions and stuff without mentioning CMB. So this is a cosmic microwave background from like way back in the day. We have a couple different maps of it, but I don't really consider the Big Bang to be like an explosion. It's more of like a rapid expansion. So this is our most updated map of the cosmic microwave background. That's kind of the first light. So early universe, there was a rapid expansion, very, very rapid, but everything was still very, very hot, very, very dense. It took a while before even atoms could form, and then eventually light could propagate. And that took about 300,000 years, 380,000 years before light could even travel. So it's not that it was dark per se, there was a lot of energy and things were hot and everything. It's a big hot mess, literally. But light couldn't propagate, and so once it could, this was that first light that's been, you know, propagating through the universe ever since. So that's what I like to think of as like a baby picture of our universe. So from this kind of initial explosion or expansion, or however you want to describe that, we have these very, very slight differences in temperature. So the different colors represent very, very tiny differences in the temperature of this radiation. So it's actually very, very uniform, which was part of like the evidence for the Big Bang Theory when we were able to measure this and detect it. That it's super uniform, but as we're able to observe it with higher and higher precision, with more and more like just more accurately and map it out, we're able to detect just these teeny tiny fluctuations in the initial temperature. And so then the question is, how did that, lead to the large scale structure that we see today? So from initial explosion or expansion, however you want to think of it, to the quasars of the early universe that are, still glowing and giving off just a ridiculous amount of energy, outshining hundreds of galaxies, to our supernovas, our old dead dying stars that outshine an entire galaxy. We have some pretty eventful stuff happening out there in space. So we'll just come back here. Thanks for joining, as always. And if you come back next week, I promise more details and better instructions for the comets. I wasn't planning on doing comets, but today I was like, oh yeah, there's comets. I should mention those. So we'll be prepared. You can practice looking in those parts of the sky. And then next week, they should just be out in the evening, basically. So we'll leave us back here, kind of near the Earth, near-ish. Wow, there's just a lot of, there's our blue ball. That's us. So again, I'm Irene Pease with the Amateur Astronomers Association. You can like us, follow us on all the social media channels at aaa.org. Sorry I forgot to talk more about OpenSpace, but again, this is OpenSpace that we've been using to fly around and observe all these data sets. Check them out. You can download it for free. And again, like I said, they just put out a new release, so that should be an exciting thing. So stay safe, and thanks for joining me for this Thursday night dose of astronomy, and we will see you next week.